My name is George Lorch, and this is Vlad Lesin. We're software engineers at Percona. And today we're going to talk to you a little bit about the head-to-head battle that everybody wants to hear about, TokuDB versus RocksDB. Which is better? So a couple of things, there's a couple of different areas that you want to look at when you're comparing these two engines. The ultimate goals of these things are to be write optimized and write efficient. So how do we measure that? Well, you want to check and measure write amplification, read amplification, space amplification to pick up the compression. And then there's also feature sets, because these are two different engines with two different levels of maturity and they're different ages. So the feature sets, really we're only going to touch on a little bit, but we're really focused here on some of the performance metrics. So how do you compare some of this stuff when you've got two engines that in implementation are so wildly different? So what we're going to do, first off, is we're going to go through a little bit of a review of what the algorithms are, how these things achieve their stated goals. And then we're going to go through the implementation implementation details of what's cached, what's the cache structure, what kind of memory it uses, how it uses memory, and then what the read and write trade-offs are going to be, and then we'll get into doing some benchmarks. So with that, Vlad's going to explain to us about the different algorithms that are in use.
Yes, the first I will start that this is not full research because we did not try all benchmarks we would like to try, and in this talk we consider only SSDs. So let's start comparison. Fractal tree. Let's consider B3. It's well known and widespread data structure. What is important here? The nodes has fixed size. Nodes contains pilots. Nodes can be not filled, and this can be the case of big write amplification. In the case of non-leaf nodes are cached, read operation takes 1 IO, write is 2 IOs, because we need to get nodes, make some changes, and then write back this node. And this is the second reason of high write amplification. And what's the best data structure for writes? If we want to improve writes, what's the best data structure? It's just login. So we could just log write operations, but read operations would be quite slow because the complexity of read operation in log is linear. So fractal tree is the try to join these two ideas, and it does hand with we have B tree, and each B tree node contains buffer. Buffer contains messages which describes data changes. And if you want to do write operation, there is no need to read leaf. May make some changes there and write it down. We just push messages in the buffer like this. And when the buffer is full, the messages are pushed down to the childs of the node. So write amplification of this data structure can be counted as k log k and divided by b, because there are k objects and all of them must be pushed down from the root to the leaves, and the tree depth is log k and divided by b. For skewed writes, it's log k and divided by b because not all objects are filled with messages, only one or several. Read amplification is the same as for B tree. For warm cache, it's 1 IO. So if we consider a log-structured merge tree, this is the idea to use a log file. But in the case of a log file, the read operation is quite slow. It's linear complexity, as I said. If we order data in the log, the complexity will be logarithmic. And but the insert complexity will be linear. The idea of log-structured merge tree is to have ordered runs, but do not do insert directly. Instead of this, there are several levels of sorted runs, and levels can be merged. Here is the example of LSM. What is important here? Each level consists of a collection of runs. Many versions of a row can exist in different runs because when we do update of some key value pair, the update is pushed on the lowest level and then merged to the next level. And if we do update of the same key value pair, the new update is pushed to the lowest layer. So there can be several versions of data for the same key in LSM. But compaction solves this issue. During compaction, these values are merged. There can be size-direct LSMs or leveled. Here we consider only leveled LSMs. In leveled LSMs, each level is limited by size. And there's such a thing as a growth factor. And in the case if growth factor is equal to 10, L1 can be between 1 megabyte and 10 megabytes, L2 between 10 megabytes and 100 megabytes, and so on. And merging happens when the size of certain level reaches its limit. Here is a merge example, and L1 and L2 are merged into L3, and we can see here that in L2 there are 10 red boxes, and after the merge in L3 there are only five merges. This can happen in the case if L1 contains updates for the corresponding boxes in L2. How can we count write amplification for LSM? The key idea here is to find the number of remerges of which the average number of remerges for the level. For example, we have two levels, L0 and L1, and when some block comes from level 0 to level 1, and then the second block is merged to the level 1. It's the first block is remerged once. When the next block is merged to level 1, the first first block is remerged once, the second is twice, and so on. And at the end, we will have that the first block is remerged k minus 1 times. The second block is k minus 2 times, and so on. And if we summarize it, we will get arithmetic progression, and we have formula to count the sum of arithmetic progression, and the sum will be k power 2 divided by 2. And if we divide it to the number of if we divide it to the k, we will get the average number of remerges for each block. And the total right amplification is the average number of remerges multiplied by the amount of levels. And this is theta k multiplied log k and divided by b. So for code cache, this great formula can be applied to count rate amplification, but it doesn't really matter if we consider warm cache. In the case of warm cache, read amplification costs several IOs. For point queries and Bloom filters, in most cases, this can be one IO. So if we compare this two data structures, we will see that they're almost the same because they have the same right amplification, the same formula for right amplification, the same thing for read amplification in the case of warm cache, in both cases for range reads and for point reads. And okay, we just considered the theoretical review. Let's consider implementation because it's it influence on performance and on amplification quite dramatically. How data is stored on disk on TokuDB and on my Rocks. Let's start with this. For TokuDB, it's log files plus block files. The important thing that the only if t is in each file. So if we have several indexes, file per index, and we want to delete the index, it's just file deleting. In my Rocks, we have already had log and the SST files. Already had log can be considered as recovery log. All tables and indexes are in the same space or spaces because there is such very interesting and very useful thing as column families, when we can have several LSMs. And store different indexes in different LSMs, and one write-ahead log for them. So if we consider a TokuDB block file, we will see that it consists of blocks of different sizes, two sets of blocks they can intercept, and why there are two sets for consistency. In the case if crash happens during checkpointing, at least one set will be consistent. And what is important here, when some block is deallocated, we don't return this space to file system, except the keys when this block is located at the end of file. And in the case if we use SSD and it's mounted with this discard option, what means that kernel can issue trim commands to SSD, and we don't return this space to file system. The corresponding trim commands will not be applied to the corresponding blocks on SSD, which can influence on of rewrite speed. And another problem is fragmentation. The blocks are big enough for compression, for example, 1 megabyte or 4 megabytes. It can be tuned. For my rocks, well, there are actually two SSD file formats, but let's consider here block-based SSD file format. There are data blocks. Key value pairs and data blocks are ordered, and there is index blocks. And what is important is that compression dictionary is created for the whole SSD file, which improve the compression quality. So if we are going to compare TokuDB and RocksDB on persistent storage, we will see that on heavy random updates, the size of block file in TokuDB can be increased, and sometimes it can be doubled. One file per index has its advantages, so we can easily drop index. And in TokuDB, blocks has good compression quality because of their size. For RocksDB, there are no gaps like in TokuDB, but on heavy random updates, there can be a lot of different values for the same key on different levels. All indexes in the same namespace or namespaces if we use column families, and SSD files are well compressed because compression dictionary is common. Let's consider how caching happens in TokuDB and in my rocks. Well, in TokuDB, there's cache table. Cache table consists of cache files. Cache files cache blocks from block files on disk. What is important here is that checkpoint can influence on I/O and on memory consumption, because checkpoint happens in two steps. On first step, all nodes are marked as pending, and in the case if some client tries to change pending node, the node is cloned, and it can lead to extra I/O and extra memory consumption. Here's the illustration how checkpoint influence I/O, and the relation between the number of the number of threads for checkpointing and the shape of the I/O curve. This is so-called constorm effect. Constorm effect if there are extra memory consumption because of not cloning. And this graphic represents the amount of consumed memory during checkpointing and the try to fix it.
Yeah.
So Lorch tried to fix it. About my rocks, there can be there's mem table with there are mem tables which can be considered as write buffers, and they are big memory consumptors. Just block cache, and by default, indexes and Bloom filters are cached outside of block cache, which can lead to extra memory consumption too. And probably the more interesting part of this talk is benchmarking. The first, I would say that it's quite hard to compare these two engines because there are different data structures and different settings of these data structures. And for example, when we tune some option for TokuDB and it influence on reads and on writes, and when we try, it does hand tune something in my rocks. The influence on rewrites is absolutely different, and that's why it's not so simple to compare these two storage engines. And apart from this, there is a MySQL infrastructure influence. Here's the example of options for TokuDB and MyRocks, which can influence on read and writes. And this is the example of MySQL infrastructure influence, and George can explain it detailed.
So in a default install of Oracle MySQL, you basically have one transactional storage engine, and that's InnoDB. When you install another transactional storage engine, that brings a whole different set of code now into play. So in the case of Percona Server or MariaDB, where you add on either TokuDB or MyRocks, you now need to involve a transaction coordinator for every transaction, because the SQL layer of the server does not know what your intentions are. It assumes that you're going to try to use both engines in the same transaction. There's no way to hint to it or disable it. So when you're using a binary log, the binary log itself, the bin log, it's treated also as a transactional storage engine, because there is a coordinator needed to ensure that when you commit, that they're in sync, right? So there is a bin log coordinator now, but MySQL actually provides two different coordinators. It provides the TC bin log, which is the coordinator anytime you got binary logging enabled, and then it also has this TC mmap. This thing is kind of a real pain, because it comes into play when you don't expect it, if you're not aware of it, and there's no visibility whatsoever that this thing is actually active and doing its thing. So whenever, and these things come into play when an engine is installed. That's all it has to be, is present and installed and reporting that it's available within the server. So the problem is TCMMap is not optimized, and it doesn't have a really good group commit implementation. Binlog has been optimized to death over the years, and it's actually it's got a great group commit implementation now. So whenever you see TCMMap coming into use, what ends up happening is you see a very large increase in syncs, F-syncs that happen while you're running your benchmarks. So within Percona Server, we're considering different options on how to address this. One is we're thinking of a session variable or some SQL grammar to allow you to initiate a transaction and tell it, I only intend on using one transactional engine, I don't want a coordinator. And then if you do try to involve another engine, we'll spit back some kind of a SQL error. The other option, and this is actually something that's now being discussed with upstream, is to improve mmap or remove it and alter the bin log coordinator to allow it to operate as a coordinator only without the binary logging functionality. So there's some options there, and we're probably going to take the first option pretty quick here, just as a stopgap, so that way these benchmarks can be run and compared side by side accurately across the variants. So do you want to continue on with that, or you want me to?
Yes, I can continue.
Okay.
So benchmarking, we decided to use sysbench because it's quite lightweight and it has great ability to write tests on Lua and to fix the current tests. And we used this ability. For this benchmark, we used the usual table from sysbench. Here's the table. We considered 4 kinds of loads. This is point reads, range reads, point updates, and range updates. And we switched off recovery logs synchronizing on each commit. So the first try. The first try actually started from reading Mark Caugan's blog posts about benchmarking. I got configs with TokuDB options and with RocksDB options from his blog posts, and here's the results. Here we can see that my rocks beats TokuDB on almost all kinds of loads. Okay, let's continue. We decided to decrease table size because it takes too long to generate 400 gigs of data. Also, we decreased memory size to keep the loads still IO bounded. The same amount of threads, but we changed the block size for TokuDB and increased fan out. For my rocks, we decreased first level size to preserve the same amount of levels per table. And here's the result. Here we can see that for point reads, the TPS is almost the same for both engines. For range reads is almost the same too. And for point updates, TokuDB beats my rocks. Range updates is the same too. Let's try to explain what's going on here. For TokuDB updates cause reads. TokuDB fan out affects read performance. The less TokuDB block size, the more effective caching, the less IOs. And for me, TokuDB range reads looks very suspicious. I expected more performance from it because range reads for fractal trees should be a little bit easier. because we have leaf node, and this node already contains the range we are looking for. And the only thing we need is just to apply my messages to this to this range. For my rocks, we tried to preserve the same the same performance as for the big table. And we started looking at my rocks, what's going on, why for range reads it's better or the same. So I don't know. It's maybe true.
Yeah, it's very small.
It's too small, but
this is we're averaging at about 120,000
yes.
reads per second in this test for my rocks.
The CPU utilization looks good, and this is TokuDB results.
And then TokuDB, there's 70,000 reads per second, yet we're still not quite as performant. So we obviously have some bottleneck internally that's keeping it throttled.
Yes, but CPU utilization looks very suspicious because the blue thing is system space. So TokuDB spends more time in system space, and this is a good reason for us to get perf or performance schema and try to understand what's going on there. And by the way, performance schema is coming soon for TokuDB. Here's the try to read write to measure write amplification for both storage engines, and it's not very honest because of two reasons. The first reason is we turned on binary logs, and that's why the absolute numbers is useless for us, and we decided to use relative numbers. So we got my rocks write amplification as 100% and counted the relative write amplification of TokuDB. And this is the results. Here we can see that for range updates, the write amplification for TokuDB is much.
It's a little
yes.
It's a less. There's a lesser amplification factor.
Yep. And this is the try to measure write amplification for the initial options when TokuDB block size was 4 megabytes and for now was 16. And in this case, we will see the same picture. This is very suspicious. Yes, because what's going on there? We would say that TokuDB. We could say that TokuDB is better than my rocks and say that we are cool. But if we try to explain this, why? What happens there? For range updates, the only thing we need for TokuDB is just push the corresponding messages to the buffer, and then these messages push down to the child buffers, and my suggestion is that. The tests, the time for the benchmarkings was too slow to see the effect when all messages were pushed down to the leaves. So if we would continue benchmark, and I don't know, the time of benchmarking would be.
You might have to go days. Even.
Yes, a few days we would see absolutely another relation.
And I believe Vadim even blogged about that at one point, something like TokuDB in the long run. And that's what it is. What happens is your tree grows out and you start getting the internal portions of the tree completely stuffed with messages that have not been delivered. So the more messages that haven't been delivered, the more work needs to be done when it comes time to query.
So this picture looks very suspicious, and the suggestion is that there's a big contention somewhere in TokuDB because of this blue part, and we tried to start benchmarks for 20 tables. And here is the results. So for 20 tables, we have quite good TPS in comparison with MyRocks. And one more thing in benchmarks, when we start benchmarking range updates, we saw the same picture. This is the transactions. This is the TPS of RocksDB on range updates. And we asked question to RocksDB guys, what's going on there, and they explained us that this is a compaction effect. This is IO statistic for this kind of load, and the same picture is for TokuDB. As we can see, the graphic is different. And again, we can explain this graphic as the benchmark didn't work a lot of time, because otherwise we would see something like this when messages would massively push down the tree. IO updates statistics. About space amplification, the initial space was the same, approximately the same for TokuDB and MyRocks. TokuDB space doubles after heavy updates. MyRocks space doubles after heavy updates too, but after compaction, the located space decreased to the initial size, to the approximately initial size. And I said that this is not finished research, and this is the items we would like to try further and share the results in blog posts or maybe on the next Percona Live in Amsterdam.
Yeah, all benchmarks, everything, this was all done with Percona Server 5.7, basically a trunk build right now. MyRocks code is in the trunk. It builds, it runs. It's just not part of any release packaging yet. We have an experimental build. But the big takeaway from that we were trying to get to, and we've been working over a year on this now to get to this point, is to be able to put the two of them side by side in the exact same environment and compare, because prior to that, the best you could do is go build Facebook MySQL and run it 5.6 and go get some other variant 5.7 and try to compare them side by side, and they're just entirely too different to really pull numbers together. So with this now, we finally have a place where we can set them side by side, work with them both, and try to figure out which is better at what workload and how to adjust them.
And I would add that don't believe benchmarks because because yes, there can be different settings and different results, and it depends on the time of testing and so on.
Yeah, there are lies, damn lies, and statistics, and as Vadim says, and I love that quote. I keep repeating it. So the thing with TokuDB too is it's out-of-the-box settings. For years, it was tuned for slow storage, for spinning disk, for high latency, but high throughput storage. The options that you would use for TokuDB in that environment are different than when you're running on SSD, and that's why we had two sets of benchmarks for almost everything, because we used the defaults, and then we also used what we've found to be the ideal values for SSD, which is smaller node size, bigger fan out. MyRocks, Mark has got some experience now benchmarking that and playing, and we're trying to achieve the same thing with MyRocks. We're trying to understand what are the optimal settings for what your backing hardware and what your workload is going to be. So as that stuff comes out for both of them, we'll continue publishing blog posts and talking about it here at Percona Live.
So and the main question of this talk wasn't answered. The question was what engine for what loads to choose. So as we can see, they're almost the same. And the only thing left is features. So maybe this can influence on your choice. TokuDB has such interesting features as clustered indexes, online index creation, gap locks, which are not fully supported in MyRocks. MyRocks has different settings for memtable, which allow you to tune your write performance. Such thing as column families, which allows you to tune parameters personally for the certain index or set of indexes. And parallel compression settings, it's a very interesting thing too, because you can, for example, for the lowest levels, use lowest compression settings and achieve best performance. So that's it.
That's it.
Yes.
Thanks for coming. If you guys have any questions. Going once. Going twice? Sold, deed. So thanks for coming. Thanks for coming to Percona Live. Thanks for listening in on us. If you have any questions in the future, you can post to our, we have got a set of forums right on the Percona website that you can ask about anything, really, any of our products or services. And if you're interested in using one of these engines specifically, you can see me afterwards. I can get you a business card and we can converse via email. So.